Hey Hawk, this is my Lab 3 Black Hole in Orbits for Physics 2211, Fall 2025. The goal of this lab has two parts. In part 1, we calculate the mass of a black hole using a star's motion. And in part 2, the goal is to calculate a velocity that lets the spaceship fly close to the black hole without entering a bound orbit. I modeled everything in GlowScript and applied three core tools: Newton's second law, F equals ma, Newton's law of universal gravitation, shown by the formula here, and the update formulas, x equals x naught plus vt, and v equals v naught plus at. I'll also reference parallel and perpendicular components of force, where the net force can be organized as F net equals F parallel plus F perpendicular. And just for reference, for part 2, if the mechanical energy is non-negative, the object is not in a bound orbit. My final results are: black hole mass is roughly 1.27 times 10 to the 34th kilograms, and a working initial velocity 2.45 times 10 to the 4th meters per second in the x and y direction, and 0 meters per second in the z direction. My model is built directly from F equals ma paired with the law of universal gravitation, which you can see the formula of here. I assume no other forces are present in space for these runs. That lets me model the gravitational interaction between the black hole and the star in part 1, and include the spaceship interaction in part 2. Numerically, I advance with the update cycle. Force gives acceleration, which updates velocity, which updates position, which updates r, and therefore the next force, repeating each time step. I also have one main assumption: I ignore other gravitational bodies because that would make the system too complicated for the scope here. For part 1, my system is a star and a black hole. Surroundings are space. Initial conditions come from the mass of the sun, the value of the gravitational constant, and delta t, the number of seconds in a day. From these values, I compute the motion step by step. In the main loop, I first calculate the star's velocity, then its momentum, and then the change in momentum to estimate the net force. Assuming gravity is the only force present, I solve the law of gravitation to estimate the black hole mass at each time step. At the end, after the final loop is completed, I report the average mass as my single final answer. For part 2, my slide defines the system as the moon, the planet, and the spaceship. Surroundings are space. The ship's initial speed is ultimately chosen by trial and error to achieve a close pass that avoids a bound orbit. The speed is part of the initial conditions, which also contain the gravitational constant, the planet, moon, and ship mass, and the given time increments. In this loop, I continuously update a distance among all objects, compute the gravitational forces between them, and then update velocity and position with the same kinematic formulas. Those updated positions feed the next force calculations, and the loop continues. I tune the ship's initial speed until the path passes close by but does not become bound, guided by the concept that a non-negative energy means no bound orbit. My main sources of error are, first, neglecting gravitational forces from other planets or bodies, and second, human error in choosing initial velocities. For what does it mean? The net force and the rate of change of momentum are mathematically equivalent in this model, but dp over dt is easier to evaluate from velocity changes, while Fnet requires accounting for every contributing force and variable. For what if? In a system with the black hole, star, planet, and moon, each body must feel forces from the other three, and I update all positions and velocities accordingly each step. By averaging the per step values in part 1, I find the black hole mass to be roughly 1.27 times 10 to the 34th kilograms. Through trial and error in part 2, a possible initial velocity for the spacecraft is shown on the slide. Other values may work as well, but this guess leads to a correct result. Thank you for listening.